get going. This is Rob Gugliemetti. He's at NREL. He's been at NREL since 2009. He's been a daylighting engineer, a lighting designer, and a lighting simulationist. He's done that in Colorado and New York, multiple places. He has over 20 years experience in lighting and specializes in physically based lighting simulation, integration of lighting and energy simulations, and application of high dynamic range imaging for better buildings. So he's going to talk to us today about some new features in OpenStudio and give us a short demo as well, I believe. So with that, I'll give it away to Rob.
Thanks, Katie. Can you guys, is this working? You guys hear me? Right on. Thanks, Katie. Thanks for coming, everybody. Yeah, today I'm going to talk about two things that we've been working on at NREL in the Commercial Buildings Research Group. I work specifically in the tools development section at NREL Commercial Buildings. So our day-to-day is focused around developing tools to do building simulation, really, is the short summary. Our flagship product is OpenStudio, and today I'm going to talk about a couple things. One is the current status of the integration of Radiance simulation capability in OpenStudio proper, as well as a fairly newish tool called OpenStudio Server, which enables you to do large-scale simulations with currently just Energy Plus, but eventually Radiance as well, on cloud resources like Amazon or a cluster or whatever. I always like to start out with the top quote. This is from the Rendering with Radiance book that Greg Ward wrote. Greg Ward, for those of you who don't know, is the guy that wrote Radiance. He's kind of the grandfather of Radiance. To nature, who gives us marvelous complexity all the while making it look easy. That is what we do all day long. That's what we try to get our computers to do, is to simulate fairly complicated physical phenomena. My particular interest is in lighting and trying to trace all the photons that are bouncing around in the room and through things and off of things is fairly complicated, but it literally happens in the blink of an eye or the flick of a light switch when we walk into a room. It's not easy what we do. And the other day I was watching The Breakfast Club, it was on TV, and John Bender said without lamps there'd be no light, so he's obviously not a daylighting guy. Really quickly, for those of you, how many of you guys have actually used OpenStudio, have some experience or familiarity with it? Most of you. Okay, well, cool. Well, really quickly, all we're trying to do with OpenStudio, first of all, it's a software developer kit, first and foremost. All the applications that you see, OpenStudio, the application, the plugin, the SketchUp plugin, the parametric analysis tool, all these things were built on top of the OpenStudio software developer kit. So OpenStudio is multiple things. It can be a little bit confusing. So I like to try to clear that up. The main point of the OpenStudio project is to get simulation happening on more building design projects, whether it's new construction or retrofit. The idea being that if we can demonstrate, particularly to the beam counters, that energy efficiency measures work, they can survive the so-called value engineering process and can actually be implemented in buildings and thereby save some energy. There are some fairly sophisticated simulation tools out there, Energy Plus and Radiance being but two. They're the ones that we focus on with the OpenStudio project that sort of sits on top of those engines and uses those engines to do what they're good at, i.e. daylighting simulation or whole building energy simulation, but mask some of the complexity to the user so that more people can be using these tools, thereby touching more buildings and saving more energy. So we're trying to put sophisticated tools that are really just the bailiwick of a select few and actually put them in the hands of all of the design build community and engineering community so that more and more buildings can take advantage of these processes. And so really quickly, they're just some screenshots of the idea behind building a simple model using, in this case, SketchUp. There's an OpenStudio plugin which allows you to make a 3D form in SketchUp and then apply metadata to that building form that energy modeling tools and daylight simulation tools understand, like wall reflectance and constructions and HVAC equipment and all those things, and export that to OpenStudio and do your analysis. You can also import IFC or GBXML, so you're not limited to just using SketchUp. You can use whatever BIM tool that you happen to be locked into and build your model there, get it into OpenStudio to conduct your analysis. Once it's in OpenStudio, this is what it looks like. It sounds like you guys are all familiar with this, but this is the application interface. The idea is that there's a tabbed interface down the left kind of walking you through the workflow from kind of high-level site information into the details of the constructions and materials, and then into the HVAC, and then what do you want to simulate, and then finally reviewing results, something like this. This is all part of the application. We're now trying to move beyond the application and enable you to do larger scale analysis on cloud resources and do some other more sophisticated visualizations that are sort of required once you have massive data sets to look at. One of the other things that we focus on in NREL Commercial Buildings tools is the notion of making energy modeling and building energy modeling repeatable and reliable using sort of vetted input. That whole notion of garbage in, garbage out certainly applies to the building energy modeling world. The results of your energy model are only as good as what you put into it and your assumptions, and so we have things such as the building component library, or the BCL, which is a, are you guys familiar with the BCL? There's a lot of nodding. That's good. So, you know, website where you can go and you can look up a couple of things. One is building components, so materials, constructions, HVAC things, etc., and also measures. And we'll get into measures in a little bit more detail as we go through the day here. But measures are basically just short scripts that modify something, one or more things about your model. So again, it's that notion of repeatability. So you can apply a measure to one or lots of buildings or a whole suite of measures, and that's pretty much what the cloud analysis tool is all about, is saying, well, I want to look at the interaction between window to wall ratio and, you know, insulation rating and, you know, building orientation. Maybe it's just those three things, and you want to, or rotate your building in 10-degree increments, or, you know, change the R value in certain number of steps. And by wrapping all that stuff into a script, you enable people to repeatedly redo that same analysis, or apply it to a huge amount of building types or locations for the same building, etc., so that your results, your data sets are a little bit more reliable, far more so than if a user started with what we call a seed model, like sort of your baseline building model, and then just did lots of save as and changed one parameter in the interface, the GUI interface, which is just an easy way to screw something up or forget something, or, you know, all of a sudden your data is all messed up because you have 3 copies of the same model, you forgot to change one parameter, or you changed it wrong. So the measures are a way of sort of enforcing standardization of your analyses. Once you have a series of measures that you want to look at in a seed model, you can throw it into the parametric analysis tool. We also call it PAT. That's the acronym. This is basically an OpenStudio interface to both your model and your measures. So this is a way to sort of drag and drop measures onto a seed model, so you can basically build up a parametric analysis. And this is a nice GUI that allows you to do that. It also gives you a history of what you've done. This was originally conceived as something that the user would run on their local machine, so you're essentially limited to the number of cores you've got on your machine. Over the last year or so, we enabled cloud capability in PAT, so that you could, instead of running it on your machine and being limited by the resources you've got there, you could send it off to the cloud. The cloud in this case being Amazon Web Services. It's widely available, it's fairly inexpensive, and again, we'll get to more of the whys about that in a minute. But that is still currently the sort of the entry portal to doing large-scale analysis. The idea here is that at NREL we have access to a supercomputer right on the NREL campus, which is all well and good for the people at NREL, but we're also developing tools to put in the hands of all the users out there. So fat lot of good the supercomputer does at NREL for all of you. So the idea here was to allow you to do the same type of analyses and not be limited by the hardware that's in your office or under your desk. Because, some of these simulations can take quite a bit of time. Having an easy interface like this, you can quickly create a parameter space that's fairly out of control, thousands of simulations pretty quickly, and that becomes pretty intractable on even your 8 or 16 core computer under your desk. So we want to give everybody access to the ability to push these things off to nearly unlimited resources. Another thing that we've been working on over the last couple of years is Radiance integration into OpenStudio. So most of you are probably aware of the simulation capabilities that are intrinsic to Energy Plus. They're not very good. They're somewhat crude, and there's all kinds of limitations on the daylight simulation capability in Energy Plus. Whereas Radiance is almost unlimited in terms of complexity of form and materials and types of analyses that you would want to do in terms of the daylighting and electric lighting analysis. So the idea here was, well, let's use Radiance for what it's good at, Energy Plus for what it's good at, merge those results through Energy Plus, through OpenStudio, again, programmatically, to give you sort of an integrated building model result. Because Radiance has different capabilities than Energy Plus, that implies that the OpenStudio model, which sort of sits on top of all of these other building models, the Energy Plus model, the Radiance model, et cetera, has to have the capability to speak Radiance or to speak Energy Plus, right? So Energy Plus, its notion of compartments within a building are really basically just thermal zones. It's all driven by what the thermal zones are. And unfortunately, that translates directly into the geometry that gets exported and calculated for daylight distribution in space. So your thermal zone boundary is your space boundary. So even if it's a big room that may be 50 feet deep with big core space that's not really getting a lot of daylight, and a perimeter zone that's only 10 feet deep because that happens to be how the mechanical system is designed, well, daylight in the Energy Plus land could never get past that thermal zone, even though there's really no architectural analog to that wall. So we create objects in OpenStudio so we can say, for example, this thermal zone boundary is just that. It's just a thermal zone boundary. It's not a wall. It actually passes through this bit of furniture in here, which also is not something that you can really define physically in an Energy Plus model. You can define its mass. You can define people loads and objects, but you can't actually put in physical geometry, things that would actually block or redirect daylight, for example. This is a huge problem. So we have objects in OpenStudio that we can put in the OpenStudio model that go to Radiance but don't go to Energy Plus. Conversely, this is a thermal zone boundary. It's not an actual wall or anything, so this does not go to Radiance when in fact it does perform its duty as a thermal zone boundary when it's talking Energy Plus. So these are all things that have been in OpenStudio for a while. We're just starting to get to leveraging some of the other things that have been added to Radiance over the last couple of years that we'd also like to take advantage of. The main thing is this so-called three-phase support. Are you guys familiar with this notion of three-phase versus single-phase versus five-phase? The idea here, this is actually a simulation methodology that was developed to enable users to do Radiance simulations that take into account the interaction of blinds. So if users actually change the blinds and change the state of the blinds from one time step to the next. So rather than having one model that you just look at all 8760 time steps hourly, the conditions of that building, whether the blinds are up or down or the slat angles have changed, they do change over time throughout the course of the day and throughout the course of the year, and that all is dependent on the user's interaction with the building. So the three-phase method basically splits the light transport problem into three phases. So there's the light coming from the sun and the sky to the window or to the building interface. Then there's a second phase at that interface which dictates what happens to that light as it hits that interface. Some of it is reflected off, some of it is transmitted through. So what happens there? So that's the transmission matrix. And then the third phase is, well, what happens now? The light that is actually passed through, where does it go into the space, and how much of it ultimately hits a point on the desk or dictates what the appearance of a specific pixel is, right? Because that's all a rendering is. It's just a bunch of point-by-point calcs, but they're actually pixels that stack up and make a nice image. We're generally concerned more with point-by-point calcs for quick and dirty stuff, but that's the idea of the three-phase. Very recently, there's been a tool called RFlux Matrix that's been added to Radiance. We've already integrated that into OpenStudio so that you can use that in your three-phase explorations with Energy Plus and Radiance. Basically, that allows you to do shading controls. You can basically say the window on the east face has a shading control on it. So something happens, that window is configurable. It can change its state. It can be clear, or it can be diffuse, or it can have a blind down, and you can define all those things. And then during the annual simulation, at every time step, that configuration can change. The distribution of that window or multiple windows can change and all contribute to a sum, an hourly sum. The other thing I wanted to talk about, hopefully if we have time, is the Radiance mirror that we have on GitHub. So this is an ability. This gives anybody the ability to download Radiance or download installers for Radiance, so that it's very easy for you to get Radiance on your computer, which historically has not been the case, especially if you're a Windows user. I'll probably just glance over that, but I did want to touch on it because it was kind of a major effort, and there's some linkage at the bottom there that gets into some of the details if I don't have time to get too into it. Really quick, I just want to kind of go through what this three-phase workflow looks like now. So this is just a real simple model. Again, we're back in SketchUp plugin land right now, and this is just a simple one zone, one space model with some skylights and an east-facing window, and the south facade is split up into an upper clear-story window and a lower window. Inside the building, we have some of those other Radiance-related objects that I referred to before. So we have a luminance map object, which basically just defines a grid of points that we want to analyze. There's a daylighting control object, which dictates what happens to the lights. That's where you can set your set point to turn the lights on or off in response to that available daylight. This is kind of the whole point of doing all this Radiance simulation. Now we're in the application, so we've done our geometry and some of the basic metadata in the plugin. Now we've opened that model in OpenStudio proper. We're in the application, and here we're looking at some of the parameters and properties. So here we're looking specifically at the window glazing. One of the things you can now specify is that the window glazing is solar diffusing. That's a yes, no. That's something that translates into Energy Plus. It now also translates into Radiance. So you can specify a piece of diffuse glass, which is more often than not the case in the case of the skylight, and that will actually properly translate over to Radiance. So it'll use a trans material in Radiance if you're familiar with the different materials, instead of just glass, which is what it used to default to. So a little bit of extra capability there. You also can assign your schedules in here. This is not Radiance specific. This is just energy model specific stuff. You need to define your occupancy, your people loads, plug loads, lighting, window shading, HVAC. Let's see. Then I already kind of touched on that stuff. You put in your photosensor points, your glare sensors. This is just the screenshot here is just showing you what an illuminance map object looks like. So this is called the Explorer. This little window here, the inspector in the application. So this is basically giving you sort of like a list view of all the objects in your model, or all the elements, and a total for each. And then on the right, whatever is selected, you get the details of that. So in this case, we've got an illuminance map objects is where you set your extents and your spacing, and that is translated directly into Radiance input automatically. We also have a tab now for Radiance parameters. If you want to wade into those very deep waters, you can, and start setting all the individual parameters. Radiance, if you're not familiar with the nuts and bolts of it, there's lots and lots and lots of different parameters that you can set to control each individual aspect of the simulation workflow in Radiance. What we give you here is that there's some presets, so you can go coarse or fine. So a coarse just means kind of in radiosity speak, it would be a coarse mesh. It sort of loosely translates over to ray tracing, which is what Radiance is based on. So it just sort of dictates how, in this case, how many rays are basically traced to figure out where the light is coming from and where it's ending up in a space. So obviously the more rays you trace, the more accurate of a result you get, but the longer you have to wait for it as well. So we give you some presets. There's also a custom option which then activates all those fields, and you can put in any parameter that you want, assuming you know what you're looking for there. And if there's any questions along the way, just please stop me. And then this is something new. This is actually a mock-up. This is not in the application yet, but the idea is that we want to, if you spend any time in the OpenStudio app, you may recognize these three tabs. This is a new one that we're mocking up for shading control, so that you can define both what happens if you do assign a shading control to a window or a group of windows. Well, what does that mean? What's the construction for the window when the shades are up, and what's the construction when the shades are down? What's the set point for making that decision to raise or lower the shades? All those kinds of things are currently being mocked up so that that can all be accessed from the GUI. Finally, this is really where all the work happens, but this is kind of like watching grass grow to actually do a demo. This is just the forward translator, which is the thing that takes the OpenStudio model and turns it into a Radiance model or project. Radiance Energy Plus is sort of monolithic. There's one file. There's an input file for Energy Plus. Radiance tends to be lots and lots of RAD files and CAL files and schedules that all kind of get munged together and piped from one command to the next. So I don't really call it a file. It's more of a project. It's a whole bunch of stuff. But the geometry, the materials, the schedules, all these things that were assumed and specified in the OpenStudio app now get translated into sort of Radiance speak. And it all happens when you just hit the run button. This is all something that just happens behind the scenes. The user doesn't have to deal with it. Some of the big things to support the three-phase stuff are that the windows all need to be grouped and simulated together. So all the uncontrolled windows, we don't need to do the three-phase stuff because they don't change their state. So we just lump all those into one problem. But then all the windows that have a shading control, now we need to look at, well, is it facing east or is it facing south, et cetera. So we lump everything together based on these, where is it? These criteria. So is it in a unique space, a unique orientation, unique visible light transmittance, distribution, is it diffuse or is it clear, for example, and is it on a different schedule than its neighbor? So all those things would dictate a separate bin. So you could have five windows facing south, and they still could be assigned different parameters, so they still get lumped further. All of these things happen automatically. Really quickly, when I was talking about this three-phase method, that second phase, that transmission matrix that I was talking about, is more often than not characterized with something called a bidirectional scattering distribution function, or BSDF. And all that is a file that basically says, for all these incoming angles of light, or for all these incoming angles, the light does this. So, if this much light hits the glass normally, X amount is reflected directly off, and this much goes through, and this much goes straight through, or this much goes diffusely through all these different directions. So it's a big matrix that just basically accounts for all the possible incoming energy and all the outgoing energy. And that's all that the BSDF does. And that's why we have to split the thing into three phases. We have to account for all the possibilities of solar energy hitting the window and leaving the window. And then in the middle there, we can just drop in a different BSDF to simulate that window is clear. Now that window is diffuse. Now that window has a blind. And those BSDFs are it's just a big matrix of numbers, but the magic that happens is that when you drop in a different BSDF to define what's going on at this transmission matrix, this is a BSDF that just says all the light just kind of comes straight through, so we have this direct sun patch on the floor. This transmission matrix is for a Venetian blind with the slats set at a specific angle to block all the direct sun. So now we don't really have anything happening on the floor. We don't have a direct sun patch on the floor anymore. A lot of it is actually being redirected up on the ceiling. And if you look at the false color images, you can also see that the amount of energy has been significantly reduced and diffused. A lot of it went right back out the window. And again, most of it kind of went up on the ceiling. So this is what happens, and this is why it's important to simulate things using a three-phase method where you actually account for people. If I was sitting at a desk right here, I would probably want to lower the blind because I've got sun in my face and I can't see or whatever. So the reality is that nobody sits in that patch of sun all day except my cat. So, I'm going to lower the blinds, which is in turn going to reduce, it's going to change the distribution of the light. A hell of a lot of it's going to go back out the friggin' window, and my lights are probably going to be on if it's a dimming kind of situation. So this is why it's important, because if you just look at a whole building energy model and you throw a bunch of weather at it and you say, well, the daylighting is great. There's daylight in there all the time. But the reality is the user's probably going to take some kind of action for half the year, while the actual daylight performance is going to be wholly different than if we just did it this way. So this is where these BSDFs come into play. And then the third thing down here, this is a daylight redirection device called a light louver. There's probably a sample around here somewhere. Takes the incoming solar energy and redirects it up onto the ceiling. So this is great because whereas this is a sort of inefficient glare control solution, this is an efficient glare control and daylight redirection system. So it actually, you can see really clearly in these images, it's taking all that solar energy and it's throwing it back up on the ceiling and it's redistributing it down. So whereas here we have a really glary type of situation that's probably going to get defeated by the user, here we have lots and lots of solar energy hitting, in this case, the floor, but in reality your task would be up here. You're probably getting 20 foot candles. The electric lights are probably off. These are the kind of things that need to get into buildings in order for daylighting to really work, to sell. And this is how you sell it, right? This is how you do it, because you can't, unless you can quantify this to the so-called value engineers, this is never going to make it. If this is just a line item, if this is something extra to buy, right, and you can't really make the value proposition for it, you're never going to see it when the building opens. So that's what we're trying to do here. So that was a little bit of a digression. But so here again is the model. So now we're saying that this is a daylight window, so it's diffuse. We're kind of treating it like the Venetian blind scenario in the previous slide. The overhead skylights are diffuse. That's kind of status quo design, right? You don't really want that direct solar path coming in. These guys are diffusing it in a much more clever way. But here we're just saying those are diffuse. There's no controls on them, so lump those all together into window group 1. Again, this happens automatically. This window and this window are both clear, and they're both the same visible light transmittance, let's say, but they're facing different directions, so the sampling problem is different. So this one's going into window group 1, and this one's going into window group 2. Again, all this is happening automatically with the forward translator. All you do is you hit the run button, and you say, look at my awesome 3-phase simulation and all this data that I got automatically. So this is just the output from the simulation running, and it's just telling it it's automatically, it's already split the model geometry into these appropriate window groups, and it's simulating and creating the daylight matrices for the different things. And what you end up with is data, lots of it. This is a really crude attempt at just showing you that the model was sort of discretized into all the different apertures that are letting light in, and this is just a visualization of the daylight illuminance on the work plane in that space for 1 hour of the day. We've got all 8,760 of them. This is just one of them. This is something Kevin and I were talking about earlier, is how the hell do you visualize and make sense out of all this data in an easy way? But that's the next thing to work on. But for the time being, this is showing you that at this time of day, those 2 skylights and that little diffuse clear story are giving you a little bit. So this is south, this is north, a little bit of light, lots of top light. The second window group, this row is for the shades up, this row is for the shades down. Again, you can see dramatically different results here. Here, we've got lots of direct sun splashing in through that clear south window. Users are probably going to lower the blinds or do something. So the reality is probably somewhere in between these two, really, for a good design, and this is how you figure that out. So this is showing the energy from that same window, but with that Venetian blind lowered and the slats set to block all the direct sun, so just a little bit filters in. Really only significant amounts right by the window itself. And then this is the same thing for the east window. We've got some light coming in. It's not as intense because it's probably not direct like it is here, where we're seeing almost 9,000 foot candles, whereas their peak is 1,000. So there's probably maybe we're getting a little bit of direct, but it's mostly sky brightness there. And then again, the user dropped the shade here. And the beauty of this is that you can mix and match. So the reality is if you had some sort of control on this blind system, this, you'd probably take the results from this window with the, this window scenario with the blinds down because there's all this direct sun coming in, there's glare, there's overheating going on. But over here, maybe the user could tolerate just the sky brightness. So you'd probably take this answer and this answer plus this answer and merge them all together. And this is what we can do in OpenStudio now. Make sort of this, play this game of mixing and matching to give you a result. This is just to show you the output. As I said before, the Radiance isn't like a monolithic input. There isn't just one file. There's lots and lots of files. And the point is, all of these things were created through that Radiance forward translator through the OpenStudio process. All you did was make your model, hit the run button. It generated all this stuff, except in the case of the XML files, these are the BSDF windows. These are pulled from the building component library. They're generic. They just describe, it just says the window is 25% clear glass. Go get from the BCL a BSDF for clear glass, 25% TVIS, and clear glass with Venetian blind. So we're making some assumptions for you. The goal is down the road that the user will just be able to pick any BSDF they want or make their own BSDFs and assign them to specific windows, or even have more than one BSDF. So you could, now in theory, you could do electrochromic glazing that maybe has multiple tint states and stuff like that. It opens up a whole lot of possibilities. Real quick, this is a screenshot of the same model again. Here's the skylights. Here's the east window. This again is what the forward translator does automatically for you. It found that this is a unique polygon. It's got a unique orientation, unique visible light transmittance. It belongs to a specific space. Therefore, it goes into its own window group and window group file. And this is what the input to Radiance looks like. This is why DOE has funded a GUI interface for Radiance people, because this is normally the way you communicate with Radiance. So OpenStudio generates all this stuff for you. And the big thing here is this line here telling that new program, RFlux Matrix, what to do with these polygons vis-a-vis sampling. So it's basically telling it this window faces east, shoot your rays that way, set up a hemisphere that faces east. This is dictating the number of bins to sample the hemisphere in. You can make that finer or coarser. Again, we are making assumptions for you. We're just using the Clem's basis, which is kind of divides the hemisphere into 145 pieces. The more pieces, the more rays you got to trace, the more you got to wait. It's always a trade-off. Yeah, Kevin.
This is by no way a leading question, so I really am interested in how much of this do you think a typical architect should need or should be expected to know about kind of what underlies the OpenStudio platform? If they want to do daylight simulation, how much do they need to know about Radiance? If they want to do energy modeling, how much do they need to know about Energy Plus? And I guess how do you see that changing over the next few years?
Well, that's like a beer 30 question, but but yeah, I believe that they should be shielded from it as much as possible, and that's really that's not. I mean, I don't mean that in a disparaging way. I mean that nobody has time to learn all this shit. You know, I'm really interested in it, so I've spent 25 years learning about it. But you know, most people just want results. They want to use a tool that gives them a result. You know, they don't want to know all about the tool. I mean, there's certain things I believe that people need to know. I got into this mess because I was using a lighting simulation tool and I wasn't getting results that I expected, and so that led me down the path of understanding light transport algorithms, for example, because I wanted to know why was there a shadow leak underneath this this is radiosity land. This is going back to the 90s, but you know, I wanted to know that stuff. But most people just walk away from it, and they say, "Well, I just want the thing. I just want to go file, new project, run, result, print report, invoice."
So I wonder, maybe somebody in the room can try to take a stab at answering my question. Maybe not now. I don't want to sidetrack the
yeah, no, that's
and at the end of the day, we have a little talk about it. Yeah, you want to do light looper, great, you have it in there. What happens when they want to do the wall aim line? That isn't
right.
You're screwed, or you have to figure this out, or you got to go to ML. and ask them to build you.
Well, that's, I mean, and that's, okay, so after this we should definitely talk, because there's, so the Radiance workshop was just a couple weeks ago, and I think that all of this new stuff that's gone into Radiance, it has led to some pretty exciting things over at LBL as well as NREL. So they have some pretty sophisticated measurement capability at LBL to take things like, not necessarily a light louver because the sample size is so big, but other things like Warima vines and things that, but like the 3M films and stuff like that that are small enough and thin enough that you could actually characterize what that thing does to the light and push that into a BSDF and actually get a reasonable simulation. And the idea of Andy McNeil showed, he showed a couple screenshots of some lighting manufacturers' websites where, like, any lighting designer today, is not being unreasonable to think that, well, I want to use XYZ, I want to use Zoom Tobal's, XYZ light fixture. They should be able to go, they know they can go to Zoom Tobal's website and look up that catalog number and pull down an IES file, which is basically the same exact thing as a BSDF, but for that specific distribution. It's a much simpler problem. The light fixture has a light bulb in it, a lamp, excuse me, and it's sitting in a reflector, and it's got a lens, and it all does some stuff, but it's kind of like it's not really like a time step problem. There's like a light bulb in there, it emits light, energy, it bounces around or through a thing and comes out in a certain distribution, and that's it. That's all it ever does. A piece of glass is sitting and it's interacting with an interior and an exterior environment. The exterior environment has a really, really bright light source that keeps moving in position in the sky relative to where that thing is. So that's a much more difficult problem to characterize. But that's where we're heading, and that's what's exciting about all this, is that Andy showed that the notion of going to Warima's website and getting a BSDF, and that's where the BCL is hopefully heading as well, is that you can go to the BCL and look up. And there are tools in Radiance that can allow you to generate a BSDF for arbitrary geometry as well. You could even use Radiance to characterize a Warima vine if you had the right measurements for all the material properties, and that's where it gets kind of messy and a little bit wiggly. And then that gets back to, well, either you put a big blanket like caveat emptor on the whole thing and all your results, or you dive in and understand it a little bit better. Anyway, yep. I'm going to skip through this, but this is more of that stuff that's going on behind the scenes. To do the three-phase thing, you have to actually have lots and lots of different materials describing all your different things, because when you're looking at the light coming in from one window, you have to black out all the other windows so that they're not contributing any energy to the space during that simulation. So all that stuff is kind of makes your head hurt a little bit when you wrap it around, but you don't actually have to worry about. This is something that nobody should have to worry about, and they don't have to worry about it if they use OpenStudio to do it. This just does it automatically for you, which is pretty cool. Kind of next steps. I was hoping all this stuff would make it into 1.5, which is coming out next week, by the way. But that train's already left the station. The developers are basically in sort of documentation mode. They were in bug fix mode 2 weeks ago, and now they're in documentation mode, so that the product that's released, 1.5.0, and on September 30th is as good as it can be. So I kind of missed the boat on that. So this stuff is probably going to make its way into OpenStudio in like a 1.5.1 or 0.2, which is more realistically end of October when we're all wearing Halloween costumes. But it's soon. It's on the horizon. In fact, some of that stuff is already done. And we're looking at better spatial results validation, visualization and validation. We talked about this earlier, and we can and should talk about this after. Cloud support for the OpenStudio server for Radiance. This is all the stuff that's on the horizon. Also, Dr. Rick Mistrick at Penn State has funding from the DOE through the Consortium for Building Energy Innovation, or CBEI project, to take the DASIM tool, which is a Radiance-based lighting simulation tool that's more focused on controls optimization. Where do you put the photosensor in space so that it actually is reading truly characteristic distribution of the light in the space, or user preference and then how do you control, how do you zone the lights, what's the right set point, what's the right algorithm so that the lights are actually responding to the available daylight in such a way that it saves energy and it doesn't annoy the occupants. So that's what he's working on. We're working on integrating that into OpenStudio as well. He's actually using that OpenStudio SDK, which I said all the way back in the first slide. First and foremost, OpenStudio is an SDK. It's software to make software. All the stuff that you're seeing are all examples of just what anybody could do with the SDK. Rick and company are making something, and they're using the OpenStudio SDK to do that. So we're going to see some more tools actually in the Radiance repository that will allow you to do more sophisticated lighting control simulations with Radiance. And hopefully we see, I think down the road, a path to using OpenStudio and the SketchUp plugin or whatever to make your model, do your basic simulation, your whole building simulation, but now maybe you have a couple of spaces and maybe they account for a lot of square footage in the space. Maybe it's a school, for example, and you've got like four different classroom orientations. And if you get those right for each class, each sort of exemplar classroom orientation, you can optimize the daylighting controls for 80% of your square footage. Well, now you take each one of those exemplar models, take them over to Rick's project, and do some really, really detailed glare and photosensor analysis that really get that right, and then pass that back to the source OpenStudio model, which then can go to Energy Plus and give you a really, truly integrated and optimized whole building result. Whew! Okay, so that was that. That was the Radiance stuff. This is a good springboard into the OpenStudio server stuff. This is also a little bit of shameless shilling for another project that I worked on over a year ago called Idea Kit. This was funded actually by your neighbors, the BPA. This was the idea of, well, what if we just do all the simulation stuff ahead of time, and then we just put like a web front end in front of it and say, we've got all these like pre-calculated results for what happens if you take your building model and you put in skylights, or you increase or decrease the window-to-wall ratio. Like kind of all that kind of parametric stuff. We did it ahead of time so that the user could just come up to a website and basically say, this is real clear, isn't it? Clear as mud. The idea here is there's a pull down to the 16 different building types in the NREL reference buildings. If you're familiar with those that we tried to characterize, everybody's nodding. Okay, so I have a school and it's in XYZ climate zone, and it's the reference buildings had 3 different vintages, so they changed the constructions and the efficiencies of things, whether it was a pre-1980 or new construction or in between. So you pick your building type, where it is in the world, where it is in the country, and when it was built, and then it gives you all these different options over here. So this is what's called a parallel coordinate plot, which is showing you all the different possibilities. Changing the window-to-wall ratio, adding daylighting controls, adding overhangs to your windows. All those kinds of things are up here. The amounts of change are on the kind of vertical axis. And then what you can do is you can select ranges for each one of these things or not, and it'll show you how many different combinations of those things meet a specific energy use intensity, which was the idea here. And the user can do that. This is all instantaneous. They can just pick, this is a retrofit project, so I can't change the window. So the window-to-wall ratio is fixed, but I still want an energy use intensity between this and this. So you can set that here, and it'll show you how many things match. Note how few lines are in this plot. Not a really rich data set. And yet, this is the cloud, this is the cluster computing resource that I use to generate the data for this website. This is my computer. This is my coworker's computer, and this is my other coworker's computer, and that's my dog. And this all ran over the course of like a 3-day weekend. I couldn't sleep because all 3 of those fans were going full blast because they were all doing simulations for this was all scripted, but it still had to be pieced out manually from computer to computer. All the results had to be merged and rolled up together. That website had to be put together by our web developer. Not a real tractable way to do large-scale optimization analysis, which is why, and I'm going to skip over this because we're running out of time. that's all I have to say about Radiance. That's my dog again. So now I want to, hopefully that's a segue into the cloud stuff, which I will start if I can find the play button. There we go. So now really quick, I'm going to talk about OpenStudio Server, our distributed analysis framework, and I have not a lot of time, but I also can stay after 1, unlike some of you probably, but I'm happy to stick around and keep going.
Plan for a Q&A at 5 of 1.
Okay.
And then a break, and we can do a few more slides after.
Okay. So I'm going to motor through this, but the idea here is that, you know, there are, as I said earlier, we've got a supercomputer, but not everybody else does. But, you know, Amazon has these, you know, crazy data centers. This is just the one in Virginia, but they've got them scattered all over the place. And, you know, the cost of accessing these vast resources is just plummeting. Is it possible to use these things? I mean, what would you do with just say 11 computers for 2 hours? It's cost you $35. If you're assuming 2 minutes per simulation, we're in Energy Plus land now, not Radiance. You could do 19,000 simulations. So I showed you the plot earlier that it had just a few lines connecting. I think there were 400 simulations for that one. Three laptop computers, you know, heating up my house and annoying my dog for 3 days, 300 simulations. You could do 19,000 simulations in, you know, 2 hours for $35. Spin these things up, push all your stuff to it, let it do its thing, get your data back, destroy those things, so the meter's no longer running on those resources, and do your, you know, do your work with your data later. These are basically the enabling technologies. OpenStudio is a big piece of this, and it's all based on open source software. So the idea is that you build your model via the OpenStudio application. You manipulate that model multiple times through these measures, which I've talked about. You can do basic parametrics via PAT. You can use that interface to kind of stack up all your different, or build your parameter space basically. But then for really large-scale analysis, on the order of thousands of simulations, we really suggest that you use the OpenStudio Server product. This is a screenshot of the application. Again, we've already talked about this, what the measures are, where you get them, but there's the idea. You start with an OSM, you run one or more measures that do something or some things to the model, whether in this case it's as simple as rotating the building, again, replicably. And then also these measures can get pretty sophisticated. You can get into mechanical systems, redesign, reconfiguration. It can be as little as changing a set point or as complex as just doing an entirely new system. And then the idea there is that you start with one model, you end up with another OSM that just has all these different bits and pieces changed in it. And there's a paper trail. Measures, again, you can get them from the BCL. That's a screenshot of the BCL. It's a searchable repository of measures. Full description of what the measure is. That's what the measure looks like. It's basically just a script. In this case, it's written in Ruby, but it's they're simple enough to, I mean, it's a programming language, but it's an interpreted language. You can open this up in a text editor and look at it and figure out what it does and probably even modify it a little bit to do what you want it to do and customize it to your heart's content. There's another screenshot, yet another of the parametric analysis tools. That's taking the measures and your seed model and defining a parameter space. So OpenStudio Server is sort of like the next step in this evolution. It's all measures based, but the idea is that you start with a spreadsheet where you have a seed model, and in the spreadsheet you fill out some fields, which looks like this, where you basically set all your different you stack up your measures in here. You set in your different parameters. This whole problem is then exported to the cloud. Again, it's replicable. I'm not going to talk about the server architecture, and I'm going to really quickly just go over to okay, cool. So I started up the cluster before I started yapping here. And so this is the OpenStudio server currently this is what the interface looks like. You go to the spreadsheet, you fill out your parameter space, but then you go to the command line and you basically just say start cluster. It reads that spreadsheet. It looks at your models. It looks at all the different measures that you want to apply, and it basically builds a very large problem to ship off to the Amazon cluster. And it starts up the cluster. And the cluster, in this case, being a server and a bunch of worker nodes. So the server is basically what collects all the jobs, distributes all the jobs to the worker nodes, which actually run all the Energy Plus simulations and kind of report the data back. With the cluster up, I can actually go visit that thing. And let's see if I can make this a little bit smaller so you can see what's going on here. You still read that? Yeah, kind of. Okay, cool. There we go. So this is a little server. Again, it's all open source stuff. It's running on the Amazon cloud that was just created automatically by a script. Obviously, you have to have an AWS account, credit card. Once this thing is spun up, the meter is running. But what it did while I was showing you all the other slides was it ran, in this case, 30 different data points. If I had checked in on this earlier, the pie chart would have shown me how many were still running and how many were completed. The nice thing is I can now go into the analysis and I can, let's see here, let's see if I remember how to do this. I can, for example, pull up a parallel coordinates plot, which building area is not very interesting to plot, so I'm just going to take that off. And so that may look familiar. That one's got a whole lot more lines on it. And this took about 20 minutes to generate while I was talking about Radiance things. And it probably cost about $4 worth of compute time to do. And again, so I can show you in real time what I mean is if I sort of constrain that one, this is electricity energy use intensity. So if I'm shooting for a specific EUI, and I can even move that around on the scale, you can see how some of the lines are grayed out now, meaning that those particular combinations of options don't get me to the finish line vis-a-vis, in this case, energy use intensity on the electricity side. You can play games with this all day long. You can constrain all different options. You can also move these around. So if this is your primary driver as EUI, you can put it over on the left, and then you can start to drill in. And the different things here were, in this case, lighting power density reductions, wall R value, just changing the wall R value up and down, shows you how many different things, different combinations will meet that specific criteria that you just constrained to. Yeah.
I don't understand the wall.
Okay.
I can see the labels and know what they all mean, but I don't understand the line.
Well, in other words, this is saying that if my target energy use intensity on the electricity side is constrained to this range, and you follow these lines around, so this is really just a graphic way of showing you that from the complete set of possibilities, that this is the subset of possibilities that would meet that goal. Now, what this all means is can be shown any number of other ways, like a table that summarizes what each of those combinations is in terms of, well, what is, option one might be LPD reduction of 10% plus an increase in wall R value by 10% or whatever. No one's expected to follow, to do this and then understand what that means over here. This is more of a way to visualize what happens to all your possibilities when you start constraining things. So a lot of the possibilities have gone away by way of graying those lines out. So those no longer apply. So it's really just a kind of a high-level summary of if you start really focusing in on or very tightly constraining a specific thing like EUI, or taking a whole bunch of variables out of the equation, like I said earlier, like maybe this is a retrofit project and you can't actually change, or it's prohibitively expensive to change the window to wall ratio. Well, you can just take that out of the equation and see what happens to your total, in this case, the parameter space. What happens to, we went from 3,000 possibilities to actually 400 that actually would get you to this particular target, in this case a UI. Does that make sense?
So it's a way to see what combinations of get into your result.
Exactly. Exactly. And this is just one of, there's 5 different visualization methods built into OpenStudio Server now. And all of this on the back end is based on the R statistical programming language. So it's sort of like Radiance in that it's open source and it's a very kind of an open-ended tool set for generating data set and also visualizing data sets. So this is just what the developers have sort of put together for now. There's no reason why you couldn't take that underlying data and do all kinds of other visualizations with it, or just basic reporting on it. Yeah.
So this looks like maybe 5 or 6 measures with 2 or 3 lines looking at different energy use results, right?
Right.
All the same kind of paper space. The line connects dots. So what 5 combinations, what measures equal a certain energy result? But you just showed how you could also move one of those measures around.
Yeah, that doesn't change, the importance or anything. It's just that's just a visualization, like an organizational visualization tool. So like maybe
that when you set up your parametric analysis tool, that it runs part of your 19,000 runs or whatever. It runs every measure in every order.
Yeah, that's a good question. That depends on the optimization routine that you use, which is all dictated by what's available in R. So you can do, and this was a simple, like a Latin hypercube simulation, but there's all kinds of true optimizations where it'll start to broadly sample the entire parameter space, but then it'll start to zero in on like, oh, this looks like a parameter that's giving us better gains in the energy efficiency area than this one. So we'll start to do a little bit more aggressive sampling. In other words, refine that model a little bit more tightly on this one particular building parameter or set of parameters. And, that leads to some of the other visualizations that are some of them are already in here. We're just sort of out of time to show them, but things like Pareto front, where you might optimize on energy use intensity over cost, and after several thousand simulations, you might start to see a clear curve of like where the sweet spot is between where spending money on more insulation isn't changing the energy use intensity of the building any, so you're just wasting your money at that point. Or conversely, you can get to this energy use intensity if you've got deep pockets and you just put PV all over the, carpet the entire building site with PV. Hey, look, we've got this energy efficient building, but at what cost? So those are the kinds of things that we've been doing at NREL for many, many years, these kind of cost efficiency optimizations, but we've been doing it with software that is not available to the general public. Whereas this is kind of like the first attempt at that kind of research grade optimization capability is available. Both the resources required to run all that stuff is now publicly available and inexpensive, and then the tools to sort of engage all those different sort of frankly, many of them are sort of research-grade tools and have the completely impenetrable interfaces to back that up, and giving anybody access to that by just going to a spreadsheet and saying, well, here's my model, and here are all the different things that I think I might want to try to play with. Show me the sweet spot.
So
did you have a question? Yeah.
Before you set up your set of information, send it to your podcast, can you kind of speak to the time commitment it takes to get that set up? It seems that person was good at it, and quickly, project nature and scale, things like that. So could you kind of describe and give some sort of a way to time commitment? The person who's really good at it is that like you don't want to talk to people like that in the country, or
Yeah, no, fair question. So are you referring to the time commitment of building the model, or
everything.
Everything.
To get ready to say, of course, I don't follow the recipe to plug into Amazon, but I understand. What does it take to get to that point? You say, okay, we're going to send everything to Amazon, it's going to cost me, let's do this big one, it's going to cost me $200 for whatever hours, and we get this massive bunch of information, and I can help with this. What's the time for you to get there? Okay, we're ready to go to Amazon. How much time do you spend?
Right. Well, you know, the tools that we're developing here are targeted at people that, you know, for example, the SketchUp plugin and just kind of the core OpenStudio application. These are targeted at energy modelers, building energy modelers that already know how to do this stuff. So it's the kind of thing. It's not necessarily a deal breaker on a project because you want to introduce, you know, this kind of more detailed optimization, you know, energy modeling optimization, right, over and above what's sort of now status quo of, well, here's my baseline building, and I'm going to try a couple different permutations and call it good. So there's really not a lot of overhead in terms of building up a big parameter space. It's loading up that spreadsheet, and again, the inputs to that spreadsheet are things that the design team is already going to know about. They're going to know that they have or don't have certain things as options, whether it's playing with wall insulation or window-to-wall ratio. I'm just using like a couple of basic examples. They're already going to know that. It's not going to take a lot of, you know, research or anything to figure out. And because the compute resources are cheap, they're probably going to be more open to throwing more possibilities at the cluster to see if they're even worth investigating. One thing I should point out, too, is that with most of these optimization tools and the visualizations that you get from OpenStudio Server, as soon as some results are available, they're immediately pushed up to the server. So the user can actually start to see as the results come in, they can start to look at these visualizations and figure out, well, where are some of the sweet spots. I mean, it's almost like watching an old school rendering where it starts out really coarse and it starts to get higher and higher resolution as the simulation progresses. It's actually almost exactly the same thing, where the results actually start out fairly coarse and the resolution starts to increase as more results are available. So the user could even, or the team could even elect to, you know, stop a simulation at a certain point and say, I've learned enough, or, you know, here's a couple of avenues that clearly are not the right way to go, and, you know, either just stop right there and say, well, these are the only things left available to us. We're going to look at these in more detail, or you know, like energy modeling is used on a project. It's used so late in the process because it's used one time on the building when it's like maybe at 100% design document phase, where it's too late to change anything anyway. Right. So what's the point? Right. You know, except at that point we're down to documenting the energy use for a lead point or a couple of lead points, right. and we're trying to get away from that. What we believe is that modeling, energy modeling, daylight modeling, has a role all the way back in, you know, in the sketch paper phase. And that's the hope behind tools like this, is that you can just kind of spitball, really, with a lot of different solutions, because we're making it so time efficient to do. Instead of, you know, we're taking the time it takes to do one model, you can do 1,000 models in the time it takes to do the one. Because you start with the one I mean, that's what I was hoping I was answering. The initial question was, you know, how much time does it take to do this? Well, it's the same amount of time that you're going to spend anyway to make that first model. But now the idea is that you can do it earlier in the design phase, and actually that one model becomes 100 models or 1,000 models, whatever it is. For $20, it's 2,000 models. And hopefully that gives some insight all the way back at that phase, where it's really important, because some of these things that we're looking at could be rotate the building 45 degrees. That's not going to happen at construction document phase. You know, these are some of the things that modeling can show you, and hopefully drive a design towards energy efficiency. It's far too late to do that in the design document phase, where unfortunately, far too often, that's when the first energy model is being constructed. And that's what, that's the hope behind these tools, is that we're pushing modeling further to the left on that continuum as a tool.
Okay. Well, we're going to take a quick break, and thank you all for coming. If you need to head out, go ahead. And if you could fill out your evaluation before you do, we would appreciate that. And we might just take a 5-minute break, and if anyone has more questions, Rob will be here. So thank you, Rob.